All right, I think let's get started. Well, hello everyone, and welcome to this April 2026 edition of the Rocky Worlds discussion, where today our special guest is Ina Plesa from DLR. Before we jump straight into the talk, I'll just remind you of the setup we use and the netiquette we ask for the Rocky Worlds discussions. Um, First of all, if you could always use your full name if you're participating in the Zoom, and please do keep muted throughout the talk. If you have any questions, that's awesome, but we ask that you hold them until the end of the talk, and then you can raise your hand and I'll call you forward. And if possible, please do put on your video when you're speaking to us as well, because it's really great to see everyone and get that participation in the Rocky Wells discussions. Um, and so, without further ado, I guess we just jump straight into the talk. I'm delighted to welcome Ina Plesa from DLR, who's going to talk to us about the interior evolution of rocky planets. And with that, I will let you take over the screen share, Ina, and please talk away.
All right, thank you very much for the introduction, and thank you very much for inviting me here. It's a pleasure to be here. I will try to share my screen. I hope you can see the full screen. I hope this works. So yeah, so as it was announced, I will talk today about the geodynamical evolution of rocky planets, and in particular, I will discuss of how to use models and observations in order to put constraints on the thermal history of these planets. And basically, when we look at the thermal history of rocky planets, let me get this starting. Yes, so when we look at the thermal history of rocky planets, planetary missions typically provide us snapshots of this thermal history. They provide us snapshots in time. Then, of course, our information becomes more sparse the longer we go back in time, from present day back to the earliest evolution of these planets. And the advantage of combining planetary mission data with numerical models is that we can try to decipher the entire thermal history. We can try to reconstruct the thermal history of these planetary bodies. And in addition to that, models can help us to guide the future exploration of these bodies in order to address basically their thermal history and the present day interior states. So basically what we're doing when we're combining this kind of models with observation is to, kind of try to put together puzzle pieces coming from modeling, coming from observations, coming from experiments, laboratory experiments on planetary conditions, from analogs and so on, and putting together all these puzzle pieces. We're trying to understand what is happening in the interior of planets through time and how the interior has shaped the surfaces and the atmosphere of the planets, of the rocky planets in our solar system. And specifically, we're looking, and we will be looking here in this presentation, at Mercury, Venus, Mars, and the Moon, and trying to understand what we can find out by combining these geodynamic models that you can see here, interior dynamics of Venus, of Mars, of the Moon, or of Mercury, and how to combine this information that, of course, in the end can help us to understand fundamental processes that are also important for our own planet, for the Earth. So in this presentation, I will go and highlight a couple of aspects of how we are combining this kind of thermal evolution models with observational data sets that we have from Mercury, Venus, the Moon, and Mars. I will go through all of these planets and try to give you a bit of an insight of how we are doing this. So let's start first with Mercury. As you can see here in this slide. So what we know from Mercury is that based on radar observation from 1965, we know that Mercury is in a 3-to-2 spin orbit resonance, meaning that it rotates 3 times for every 2 revolutions around the sun. And in addition to that, Mercury has another peculiarity, namely that its rotation axis is almost perpendicular on the orbital plane, meaning that the planet has a very low obliquity that induces large latitudinal variations of temperature between the polar and equatorial regions. And this, of course, leads to a very peculiar surface temperature pattern. And what we will look at here is what does it mean for the interior of the planet. So for that, what we are doing is to combine geodynamic models of the interior of Mercury. We're combining these models with taking into account surface temperature variations, as you can see here on this plot, with the two hot poles around the equator and, of course, much colder temperatures around the geographical poles of the planet. And we're also combining this with crustal thickness variations. And these crustal thickness variations come from gravity data that has been acquired from MESSENGER. Here you see several of the models that can fit the gravity and topography data that has been acquired by MESSENGER. And here specifically, we're focusing on this specific model, model D0. So we're combining our thermal evolution models with these surface temperature variations and crustal thickness variations. We do have the crust of Mercury being enriched in heat-producing elements. We take into account the blanketing effect of the crust. The crust has a much lower conductivity compared to that of the mantle, which provides this kind of blanketing effect. We're using in our models temperature and pressure dependent viscosity, and of course, we're accounting for core cooling and radioactive decay, as it's of course appropriate for a thermal evolution. And putting all these ingredients together, we can actually describe the thermal history of the planet. Here you see the temperature profiles from the surface down to the core mantle boundary for different geological regions on the planet. And here specifically you see these large geochemical terrains that have been mapped and have been observed by MESSENGER, like for example, the high magnesium region here, the Caloris Basin here shown in red, and the North Volcanic Plains, as well as some smaller geological regions. And what you can actually see here in the temperature profiles of these geologic regions compared to the solidus temperature, so to the melting temperature, is that these regions probably have experienced a very different thermal history in their past. What we observe when we look at the CMB heat flux and at the surface heat flux, these are maps shown at present day, is that the surface temperature has a strong influence on the distribution of the heat fluxes, and also the crustal thickness variations can be actually observed at a much more scale in these maps. So basically the long wavelength pattern on these maps that you can see here, both on the CMB and the surface heat flux, is controlled by the surface temperature, whereas the smaller wavelengths are more related to crustal thickness variations. So just as a reminder, this was the surface temperature pattern. This is the present day 3-2 spin orbit resonance that leads to the surface temperature pattern. And then you can, if you squint your eyes, you can actually recognize this longer wavelength from the surface temperature onto the surface heat flow maps. And we observed this for all of our models. Here, specifically a model where the crust is about 1.6 times more enriched in heat-producing elements compared to the mantle. This effect is even more visible for models where we have a much higher enriched crust, so 10 times more than the mantle. You see again this long wavelength pattern from the surface temperature, and you see smaller scale variations that are typically related with the crustal thickness. Now, as I mentioned before, we have this geochemical terrains on Mercury, and what we see in our models when we plot the temperatures over time of these geochemical terrains, again here shown in terms of temperature profiles, is that these geochemical terrains most likely have experienced a very different thermal history. We see here the North Volcanic Plains. They correspond in our models to a relatively low or cold mantle temperature. The high magnesium region is shown here in green color, denote some of the hottest zones in the interior of Mercury. The Caloris Basin, shown here in red color, is more closer to the average temperature that is shown in black color. So basically, these regions could have experienced very different thermal histories. Now, what we can also do from our thermal evolution models is to calculate the elastic lithosphere thickness. So basically, the thickness of the elastic layer that's of the layer that can deform elastically when subjected to loads like, volcanic features or basins and so on. So here what you see is the elastic lithosphere thickness over time. And here you see in symbols different estimates coming from the literature. And in color here, you see the range of elastic lithosphere thicknesses that we obtain in our models, depending on the rheology of the mantle that we assume. So basically here in orange color, a dry rheology, whereas in blue color, a wet rheology. And here in the middle, you see the corresponding elastic lithosphere thickness maps with the variations in elastic thickness over the surface plotted into a map, a surface map of Mercury. And then here the corresponding temperature profiles at the exact time that is indicated here by the red arrow. And what we see is that the elastic thickness also very closely correlates with the surface temperature pattern at longer wavelengths, and at shorter wavelengths is affected by the crustal thickness variations. And here you can see in time, the elastic lithosphere thickness increases as the planet cools and the lithosphere itself starts to grow. And towards present day, our models show a relatively cold interior, almost conducted interior that suggests that Mercury might not be in a convective state. So just to conclude this first part about Mercury, what we have seen is that the temperature, the mantle temperature pattern, the surface heat flow, also the CMB heat flow, elastic lithosphere thickness, all these quantities seem to be controlled at large scales by the surface temperature pattern, whereas at smaller scales, the crustal thickness seems to be important. In terms of the geochemical regions, these geochemical regions seem to denote different thermal histories. And we see that the surface temperature variations, they influence even the CMB heat flux, as you can see here on this map. And this might have important implication for dynamo models. So this needs to be tested in future by dynamo models to understand the effect of such a CMB pattern for the dynamo generation. And of course, the future measurements by Bepi Colombo, which will go in orbit around Mercury at the end of this year, will help us to drastically improve our understanding of the thermal evolution of Mercury. So we're all looking forward to the new discoveries by Bepi. Now, I will go into the next terrestrial body, now here looking specifically at Venus. And Venus is probably one of the most extreme terrestrial planets in terms of volcanic features. Here you see a map of Venus with, in color shown in symbols, a recent catalog derived by Han and Byrne in 2022. And this catalog comprises more than 85,000 volcanic features. So basically, you barely see a region on Venus where you wouldn't see a volcano. And that kind of tells us something about the evolution of the planet. It tells us that volcanism probably has played an important role during the thermal history, and then it may still play an important role today on Venus. Now, in terms of the volcanic activity, there are several lines of evidence that suggest that Venus might still be volcanically active at present day. And this is, of course, an important thing because Venus might be the only planet, a rocky planet, in addition to the Earth, where we could observe an active eruption. The lines of evidence that suggest this are the variations in SO2. Here, a plot from Emmanuel Mark's paper in 2013, where you can see the SO2 variations between Pioneer Venus Orbiter and Venus Express observations. And these have been attributed to potentially be linked to volcanic outgassing. Another piece of information that we have from Venus Express is the emissivity data. Here specifically, the emissivity data here shown at Idun Mons, one of the volcanoes on Venus, where the emissivity data is indicative of fresh lava flows. so perhaps linked to a fresh eruption on Venus. And one of the most compelling lines of evidence for perhaps an volcanically active Venus at present day comes from the reanalysis of the Magellan data, here shown in this plots here. If we squint your eyes, you see that these two plots here represent the same region, and the data was acquired by Magellan 8 months apart from each other. And if you look very carefully, you see some changes in the surface between these two observations. And these changes have been attributed to a volcanic eruption and the formation of a new lava flow here that you see here on the lower plot. Now, in addition to these observations, what we also know about Venus comes from gravity and topography data, and gravity and topography data has been used to estimate the elastic lithosphere thickness of Venus at different location, a different geologic location on Venus that you can see here on the left-hand side of this plot. So here you see different geologic features like coronae, pancake domes, rifts, and so on, where this kind of estimates have been derived. And what we can do is to go to recalculate the elastic lithosphere thickness into a thermal gradient. This is what we have done here. And you can see quite interesting fact. If you look very closely, you see that some of these regions, they do seem to have a relatively high thermal gradient, like 40 Kelvin per kilometer or even higher. And this kind of tells us that something is happening in the subsurface of Venus in order to be able to sustain such a high thermal gradient. Now, what we are doing in terms of thermal evolution modeling, we are looking into Venus geodynamics over the entire history, and we're looking specifically here for partial melt production in the mantle and melt extraction. Here we are distinguishing between different scenarios. So when melt is being produced in the deep interior, this melt is being extracted to the surface, and if it's entirely extracted to the surface, we talk about an extrusive magmatism scenario, whereas if a melt is partially extracted at the surface and partially intruded in the subsurface at the base of the crust, for example, we are talking about an extrusive and intrusive magmatism scenario. And I think to some extent this has been also mentioned in the seminar by Diogo Lorenzo several weeks ago, when talking about this kind of processes. Now, what we do in this kind of models is to look to vary the intrusive to extrusive ratio, but also the depth at which we place the magmatic intrusions and see which models are best compatible with the high thermal gradient on Venus as is required from the elastic lithosphere thickness, at least locally. So here I'm showing two different simulations, two different models that are identical apart from the way that we extract the melt. So in the top model here, what we do is to extract the melt, whatever melt is being formed in the interior, to extract it at the surface. So it's a fully extrusive case. And in this fully extrusive case, what happens is that we place the melt at the surface and we have this downward advection of material that leads to a very thick and cold lithosphere, as you can also see here on this plot, looking at the viscosity close to the surface. In the other scenario, only 20% of the melt that is produced in the interior can reach the surface, whereas the rest of 80% remains intrusive at about 45 kilometers depth. And what is interesting to look or to see here is that you start having regions with very high thermal gradients. These are the regions where the melt is being trapped in the subsurface, and that melt cools over geological timescales in a conductive way. So by heat diffusion. And what we can see here is that basically comparing these two models with the observed or with the inferred thermal gradients on Venus at different locations, we can actually exclude this fully extrusive model, because in this case, we won't be able to match, at least locally, not even locally, the very high thermal gradients that we have as being suggested from the elastic lithosphere thickness. So what we can say from our models is that more than 60% of extrusive magmatism cannot explain the very high local thermal gradients. So that would kind of tell us that Venus perhaps is in a regime, in a geodynamic regime, the so-called plutonic squishy lid regime that I think Diogo also mentioned in his talk, basically being the dynamics in the subsurface and interior of Venus being driven by magmatic intrusions and the lamination of the surface. Now, in addition to magmatism, we have also other information about more deeper interior of Venus, and this comes from tidal deformation. We have estimates of the tidal of number K2 that has been determined by using gravity data acquired by Magellan and Pioneer Venus Orbiter. And in terms of the phase lag, so the lag of this deformation, this has never been measured for Venus. This is something that the new Venus missions, Veritas and Envision, will do. But we do have right now some theoretically inferred values placing the tidal quality factor that is describing this lag of the deformation between 20 and 100. Now, this lag of the deformation, typically rocky bodies, they don't, if you would have a perfectly elastic body, you would have instantaneous deformation when subjected to tides. But of course, rocky bodies are not perfectly elastic, so that's why we have this lag in deformation that can be measured from missions, from orbiters. So what are we doing here in order to use this kind of information, additional information for the deep interior of the planet, is to combine our geodynamic models with models that are computing tidal deformation in order to understand which parameters, which thermal evolution can match these, the observed or the measured value of K2 and the theoretically inferred value of Q. Now, the size of the core affects the tidal of number K2. So the tidal of number K2 is sensitive to the size of the liquid core. And this is important because then we can use our models using here different core sizes, as you can see, from 3,025 kilometers, so about half the planet radius, up to 4,000 kilometers here. And what we can do is to compute the tidal of number K2 for all these models and see which ones are actually matching the measured value. Here again, the tidal of number K2 is shown on the y-axis in black line, the average value, and in gray the uncertainty. So we have quite large uncertainties right now in the tidal of number K2, but this will improve with the upcoming missions. And what you can see here is the tidal of number K2 calculated based on our thermal evolution models, based on the present day thermal state and viscosity of the interior. So here what you can actually observe is that with increasing core radius, we also increase the tidal of number K2 results. And we see that for models that have core radii about 3,750 or larger, they are already outside of the range of the tidal of number K2 values that we have currently for Venus. We still have large uncertainties on the core size based on these estimates that we have right now. And as I mentioned before, this will improve with the next missions to Venus, Envision, and Veritas. And you can see here the expected accuracy with which we would be able to determine the tidal of number K2. And this will, of course, provide us a much better constraint on the interior structure of Venus. For the phase lag, the tidal quality factor Q is dependent on the viscosity of the interior. So the depth dependence of the viscosity affects the phase lag of the tidal deformation. And here, what we have done is to use our models to compute here the present day viscosity structure of the interior using different viscosity increases with depth. And you can see here in terms of the tidal quality factor or the phase lag, how the tidal quality factor, for example, changes with increasing viscosity with depth. And basically, as I mentioned before, we don't have measurements of the phase lag or the tidal quality factor for Venus so far. We have only theoretically inferred values that place the tidal quality factor Q between 20 and 100. So basically here, all these models would be compatible with the theoretical inferred values, but we would require, of course, a ground truth measurement in order to understand better what the viscosity structure in the interior of Venus is. And this is going to be done by Envision and Veritas. And here you can see the uncertainties with which both Envision and Veritas will be able to constrain the tidal quality factor Q. So here this is only showing the uncertainties for a specific example. This range can lie anywhere here on this plot. But is to show that with future measurements by Veritas and Envision, we will have a much better constraint on the viscosity structure in the interior of Venus. So just to conclude also this part, what we have seen is that based on the models that we are doing is that the intrusive magmatism is actually required in order to explain a warm lithosphere, at least locally, as it is indicated by the elastic lithosphere thicknesses. What we have also seen is that models with relatively large core radii, larger than 3,750 kilometers, based on our models and current K2 estimates, are incompatible with observations, but of course we will have much better constraints from the future missions to Venus. From our models, we see that the viscosity contrast with depth, so the increase of viscosity with depth should be less than about 500 in order to be compatible with theoretically inferred values that we have for the tidal quality factor. And as I mentioned before, missions like Veritas and Envision will advance our understanding and provide much tighter constraints for the interior structure and thermal state of Venus. So now let's go quickly to the moon. Here on the moon, we have a very special situation. We know that the moon has had a magma ocean in its early evolution, has been characterized by a magma ocean, a liquid magma ocean in its early evolution. And this magma ocean started to crystallize with time. So here you see a sequence of this crystallization. And basically what you can observe here is that after about 80% of the mantle of the moon has crystallized, we are starting to form the so-called plagioclase crust, this anorthositic crust, this flotation crust basically that is where material that is crystallizing is lighter, rises to the top and forms this light crust that we see today on the moon. And by further advancing the crystallization sequence, what happens is that in the end, we have this very thin layer that is extremely enriched in heat-producing elements, the so-called creep layer. So creep stands for potassium, rare earth elements, and phosphorus. And this creep layer is basically sandwiched here between the crust and the underlying mantle. And we think that, this global magma ocean stage has basically characterized or has helped to, affected the entire subsequent lunar evolution. So this creep layer that I have mentioned before, this is typically the last product of the lunar differentiation and is thought to be located between the crust and the mantle, is high in heat-producing elements, so thorium and uranium, and therefore provides a local heat source in the subsurface of the moon, and has been proposed to also explain the lunar asymmetry. The lunar asymmetry here in terms of the distribution of heat-producing elements, here specifically thorium on the surface of the moon with this very high enrichment in thorium on the near side, on the lunar near side compared to the far side, as well as volcanic activity on the moon here with the youngest basalts being located, and most of the basalts being located on the near side compared to the far side. And the presence of this enriched layer, the presence of this highly enriched layer in heat-producing elements, of course, can affect the surface heat flux, because the surface heat flux is sensitive, especially its variations are sensitive to the distribution of heat-producing elements in the interior and in the subsurface. Now we have estimates, we have measurements of the heat flow on the moon. We have the Apollo measurements, Apollo 15 and Apollo 17, here located on the lunar near side, close to this, within or even close to the PKT region, to the Procellarum creep region, this region that was highly enriched, in heat-producing elements. We have some more estimates coming, however, from remote sensing, so probably associated with large uncertainties. These are the Compton-Belkovich region here, close to the lunar South Pole, and the region 5 here at the lunar South Pole, and here Compton-Belkovich close to the lunar North Pole. And there are two new in situ measurements that have been performed or are going to be performed in the near future. And the values at Mare Crisium and Schrödinger basin, these are the two new in situ measurements that we're expecting. There are some early estimates here for the Crisium region with a heat flow lying between 13 and 14 milliwatts per square meter. And this is important because we can use this kind of heat flow measurements in order to constrain our global thermal evolution models. So in order to do so, of course, one of the questions is how is the heat production distribution in the subsurface of the moon, so in the how is this creep layer distributed in the lunar interior, because this of course can have important implications for the heat flow estimates. So how are we going to test this with our geodynamic models? Here we're looking again at 3D global thermal evolution models that we again combine with crustal thickness variations. You see here one of the crustal thickness models that has been derived based on gravity and topography data for the moon. And we are also assuming a heterogeneous distribution of heat-producing elements in the lunar interior. Here, kind of like a sketch showing the crustal thickness in red, and in yellow colors the heat-producing elements that can be distributed either sandwiched between the crust and the mantle, as you can see here in a so-called heat-producing elements anomaly, or distributed, of course, homogeneously in the mantle. And what we're doing is to run our thermal evolution models, compute the distribution of surface heat flux at the specific locations that we saw on the previous slide, and to understand which models match best these observations. So here I'm showing several scenarios that we have tested in a recent paper that has been published last year. Here specifically, there are 3 categories of models where we have symmetric distribution of heat-producing elements in the sense that they don't vary laterally. So here in the first case, we have a homogeneous layer, creep layer, just below the crust, sandwiched between the crust and the mantle. In the second, symmetric distribution is assuming that we have remixed this creep layer, the heat-producing elements, back into the mantle. And then we have two other distributions that are heterogeneous, one of them assuming that we have a hemispheric distribution of heat-producing elements in this creep layer beneath the crust, and another one assuming that we have actually a regional one, so much smaller anomaly in terms of its extent. And the distribution of heat-producing elements in the subsurface affect, of course, substantially the temperature in the interior of the moon. And I'm showing here temperature variations in the interior of the moon, with red colors showing temperatures higher than average, and blue colors temperatures lower than average. So, of course, in a symmetric distribution, you kind of see a more kind of like homogeneous distribution of temperatures. But as you go into this asymmetric distributions, you see here a dichotomy in temperatures between the lunar near side and the lunar far side, and here a strong temperature anomaly beneath the PKT, the Procellarum creep terrain. And what we can say about these models is that for models with symmetric heat-reducing elements distribution, these are incompatible with the Apollo measurements because they would give us too low heat fluxes compared to what we have in terms of observations. For the hemispherical anomaly, for the hemispherical heat-producing elements anomaly, we can explain the Apollo values. And in terms of the south polar heat flow values, we would get similar values to those as measured at the Apollo landing sites. Whereas in the regional scenario, what we can say here is that the Apollo, we can match the Apollo values, but at the same time, we have much lower values at the South Pole. And in this case, we would require a relatively weak heat-producing elements anomaly beneath the PKT, beneath the Procellarum creep terrain, with about 30 ppm of thorium and 8 ppm of uranium. So when we are looking at the surface heat flow maps that we get from this kind of models, this is what you would expect. Here again, the Apollo measurements, the Crisium and Schrödinger crater locations, and the region 5 here at the South Pole. So what we can say in terms of our models that match the Apollo measurements is that they require a low concentration of heat-producing elements in the bulk silicate moon, about 16 ppb of uranium, and they also require a low heat-producing elements concentration in the in this anomaly that you see here, about 30 ppm of thorium. And in terms of predictions, what these models, our best fit models predict is that we have a lower heat flow at the South Pole, about 9 milliwatts per square meter. This is, of course, higher than what was been suggested by the region 5 observations or measurements. However, keep in mind these measurements are being derived from remote sensing observations, so potentially they are associated with large error bars. And in terms of the measurements at Schrödinger crater and Mare Crisium, these are the ranges that our models predict. And if you remember the Mare Crisium estimate, it was about, so the early estimate that we have now is about 13 to 14 milliwatts per square meter. So it's actually quite a nice match. We do have models that fit quite well both the Apollo landing sites and some of the earliest estimates for Mare Crisium. And what we can conclude from this is that in order to explain the available heat flux constraints that we have for the moon, we would require at least a local, at least a hemispherical, but more likely a local creep extent, so heat-producing element layer extent in the subsurface. We see in our models that we don't require such a high concentration of heat-producing elements in this anomaly. So most of our models are compatible with a relatively low heat-producing elements concentration in this anomaly. And of course, right now, the uncertainties associated with the estimates that come from remote sensing are somehow kind of like a bottleneck for our models, preventing us to further constrain the distribution of the heat-producing elements in the interior of the moon. But of course, the values that we will have and that we have from Mark-Crisium, that we will have also from Schrödinger measurements, they will help us to further constrain and further tie in the possible scenarios for the heat-producing elements distribution in the interior of the moon. And now I'll just quickly go to Mars. On Mars, of course, we know that based on geological estimate and mission data from Mars, we know that that Mars has been volcanically active in the past, and that volcanic activity has decreased with time and has become more focused in two of the large volcanic centers that we have on Mars, the Tharsis region that you see here and the Elysium region here. So in these two regions, we have very young lava flows that kind of tell us that Mars might have been volcanically active into the recent past, several million years ago. Here is an inset of the Elysium region, and specifically here we see the Cerberus fossae system of fractures, where we have some of the youngest lava flows that we observe on Mars. And this is, of course, an indication that, potentially mantle plumes could still be present in the interior of Mars and could still produce partial melting in the interior of Mars at present day. So this kind of suggests that, the interior of Mars is relatively warm in order to sustain this prolonged volcanic activity that we observe in being more and more focused over time in Tharsis and Elysium. But at the same time, we also have other constraints coming from the elastic lithosphere thickness estimates that are available at a variety of geological locations on Mars, as you can see here on this map. Of course, they are associated with large uncertainties, especially for volcanic centers, where these volcanic centers have been built over time. So the load that has led to this elastic lithosphere thickness values has been growing with time. But perhaps the most important estimates that we have here in terms of the elastic lithosphere thickness are at the north and south pole of Mars, because these two are associated with the age of the polar cap of Mars. And we know that the polar cap of Mars are relatively young, specifically the North Pole here. And the elastic lithosphere thickness at the North Pole has been suggested to be relatively large, more than 350 kilometers, which would be indicative of a very thick and cold lithosphere. How this has been estimated, the elastic lithosphere thickness at the North Pole is basically using radar data over the North Pole here, acquired by Sharad and Marsis. And you see here the radar spots, the radar data that have been acquired. And what this data shows here is basically a radargram showing the North Polar cap. And you see here the surface beneath the North Polar cap. And what you can observe if you look very closely is that the surface has not been deflected underneath the North Polar cap, so has not been affected by the load of the North Polar cap. And that requires that we have a relatively thick and cold lithosphere in order to, to sustain the load from the polar cap. So while before I was telling you that, we have indications that Mars have been relatively warm until recent times in order to explain young volcanism, this constraints that we have here tells us that at least regionally, at least locally, the Martian interior must have been or must be relatively cold in order to support this loads that we have on top of the surface. So what we are doing in order to test which kind of parameters are compatible with these two contrasting constraints is to run geodynamic models that include spatial variations in crustal thickness. Here's a crustal thickness map that has been derived from gravity and topography data, and also anchored at the InSight location by seismic measurements. So Mars is, apart from the Moon and the Earth, the only terrestrial planet where we have seismic measurements, and they help us, of course, constraining the interior of the planet. Now, what we're doing in our models is to investigate how crustal thickness variations affect the thermal evolution and the present-day thermal state of the interior, and specifically focus on those models that are compatible both with estimates of the elastic lithosphere thickness at the North Polar Cap and as well as recent volcanic activity. So when we put all these together, here's a range of temperatures shown in orange color that is actually compatible with both large elastic lithosphere thickness at the North Pole and compatible with present-day melting, at least locally in Tarsus here and in the Elysium region. And if we compare these temperatures with the temperatures estimated based on seismic observations, necessary to fit seismic observations, we see that they are pretty well compatible, perhaps a bit at the upper end of the seismic data, seismically inferred temperature data. And what these models tell us is that melting can still occur in the interior at present day in very localized areas, as you see here on this map beneath Tarsus and Elysium. Now, what these models have in common is that their temperature variations in the subsurface closely follow crustal thickness, the crustal thickness pattern. If you remember the crustal thickness map of Mars, we had a much thicker crust on the southern hemisphere compared to the northern hemisphere. So we have this dichotomy that we can observe in the temperature field up to 400 kilometers depth or even more. And this, of course, also has an effect on the seismic velocities. Here you see seismic velocities maps, here specifically the shear wave velocity variations and the shear wave velocity gradient, starting from 200 kilometers depth down to 700 kilometers depth. And what you can clearly see here is that also the seismic velocity variations in the interior of Mars, they closely follow this dichotomy in crustal thickness. And you can see this pattern extending up to 400, 500 kilometers depth. Here you see a profile of the seismic velocities that we get from these kind of models. And what you can observe that the strongest variations in seismic velocities are acquired just below the crust in the lithosphere, where we have the strong variations controlled by the crustal thickness variations, and of course at the location of phase transitions here, specifically from olivine to Watt's-Laet. Another information that we have from InSight based on the seismic data from InSight is about the Martian core. So using seismic measurements from InSight, we determine the size of the Martian core, of the liquid core of Mars, and this lies at about 1,830 kilometers plus minus 40 kilometers. And this kind of requires a high amount of light elements in the core in order to match the mass constraints for the planet, in order to match the mass of the planet. And such a large core is also important for the mantle, because in the end, the size of the core determines the thickness of the mantle. And what we can see is that this large size of the core kind of excludes having a Bridgmanite-dominated lower mantle on Mars. So having an endothermic phase transition similar to the 660 kilometers phase transitions on the Earth at the base of the Martian mantle can no longer occur based on the pressure associated with the pressure in the mantle that is, of course, constrained by the size of the core. Here you see three different models with core radii ranging from 1,500 kilometers to 1,850 kilometers. And here's just to show how the pattern of temperature, so here you see the temperature at 100 kilometers above the CMB and the temperature in the mid-mantle. The yellow regions show the hot regions in the mantle, so basically the mantle plumes. And you see how the pattern changes by increasing the core radius. So at the moment, these are the preferred models with a core radius of about 1,850 kilometers, which is within the range of the core size determined by InSight. And what we can see in this kind of models is that the pattern becomes dominated by a number of plumes and downwellings, but some of the strongest plumes are located beneath volcanic centers like Tarsus and Elysium. So also to conclude this part here, what we have seen for Mars based on these geodynamic models and combining them with the observations that we have for Mars is that only a limited number of models are able to fit available constraints, and they require a crust with a substantial fraction of heat-producing elements, that the temperature variations and seismic velocity pattern follows, they correlate with the crustal thickness dichotomy. And here we would definitely need more geophysical measurements in order to further constrain the interior structure and thermal state of Mars in order to decipher its thermal history. So basically, just to come back to the puzzle that I was showing before, I hope I was able to give you an overview of how we combine this kind of global thermal evolution models, geodynamic models, with observations in order to shed light on the processes that happen in the interior of rocky planets such as Mercury, Venus, the Moon, and Mars, and then in the end to understand how how physical processes affect their interiors over time, but also their surfaces and atmospheres that we observe today. And with this, I'll end here and be happy to answer questions.
Okay, thank you, Ina, for a very fascinating talk. If anyone in the chat has, sorry, anyone in the call has questions for Ina, please just raise your hand and I can call you forward. And if there aren't any yet, I guess I can kick us off and start with one. I was wondering about what you think about the potential for extrapolating some of these models to other satellites further out in the solar system. So we have some rocky satellites and we have some rocky/icy satellites. I was wondering what your thoughts were on how we can use these kind of models to explain observations on those worlds and the additional challenges that may come about from having a very large ice proportion, for example, close to the surfaces of these worlds.
Yeah, very good question. Thank you. So in this talk, I focused specifically on rocky planets, and of course, Moon I counted as one of the rocky planets. But what we can do with this kind of models is also to look at icy satellites. And of course, icy satellites are a bit more exotic in terms that you have a rocky well, you can have an iron core, you have a rocky core, a rocky mantle, you have the ocean, and in some of them you have high pressure ices, you have in others you have only the outer ice shell. But the models that I've presented here, they can be adapted in order to model especially processes happening in the outer ice shell of Europa or on Enceladus, on Ganymede, in the high pressure ice layer of Ganymede, to track the evolution of temperature, to track melting, for example, in the ice and where that melt is transported. And also, of course, naturally, they can be applied to look at the rocky part of these icy satellites. So this is actually work that we are also doing in our group here at DLR, specifically looking at the ice shell of Europa, Enceladus, and Ganymede, also in the perspective of the upcoming missions to these icy satellites, specifically the JUICE mission and the Europa Clipper mission that will, of course, revolutionize our understanding of processes on these icy bodies.
Great, thank you. We have a question on Zoom. So, Redas, am I pronouncing that correctly? Please go ahead and ask your question.
Yes, you showed a couple of models with lateral heterogeneities, in particular for the Moon and Mars. And can you tell us a bit more about how these heterogeneities form? I mean, for the Moon, for example, you prove that you need this heterogeneous distribution of creep material, but how does it form? Is it imposed, or does it somehow evolve from the setup of your models? That was not clear to me.
Yeah. Oh, okay. Thanks, Thomas. Thank you for the question. So what we have in these kind of models, what we do, we start our models at the end of the lunar magma ocean crystallization. So for us, this heterogeneous creep layer that I've shown on the moon that you just mentioned is basically kind of like a free parameter, if you want, in terms of its extent, right? So we have the extent of the creep layer, assuming that is homogeneously distributed under the lunar crust, or only hemispherical in extent, or just regional in extent. And this, of course, affects the way that the temperature evolves in the subsurface of the moon, and of course, how the heat flux then in the end varies over the lunar surface. For us, as I said, the start point of our models is the end of the lunar magma ocean. Of course, there are models that are looking at the lunar magma ocean crystallization, and they look at how the mantle crystallizes, how this layer forms beneath the lunar crust. But as I said, our models, they start already when that layer has already formed, and this is present in the lunar crust. And then we have to make some assumptions, right? So if we have, for example, what we have tested in our models is whether this layer is homogeneously distributed beneath the crust or homogeneously distributed in the mantle. So assuming that, through additional processes, this layer has been remixed back into the mantle, or only parts of this layer has been remixed back into the mantle. So we vary these kind of parameters in order to understand which models for which layer extent and heat producing elements within this layer we can actually match the surface heat flux constraints. And this kind of gives us an idea of how this layer is distributed, at least at present day.
So, but that implies, of course, that the initial inhomogeneity has indeed formed that early.
Yes, exactly. So how this initial heterogeneity has been formed, it's a whole other question, and there are a lot of studies and a lot of suggestions how this might have formed, whether it has been, an asymmetric crystallization of the magma ocean, or driven by an impact. South Pole Aitken impact basin has been, correlated or related to the fact that it might have driven this, the mixing of creep on the lunar far side within the mantle. Or some combination of these two. So there are different scenarios out there that I think, addressing this kind of formation of the initial heterogeneities. But for us, we start already assuming that this heterogeneity exists.
Okay, thank you.
Thank you, Thomas.
All right, maybe time for one more question. Claire, if you want to ask away.
Yeah, thanks. Yeah, great talk, Ina. I was wondering, so you say you need to have a lot of intrusive magnetism on Venus to match the heat flow. So I was wondering, is there anything mechanical in the lithosphere that actually controls this ratio of extrusive to intrusive magnetism? Or is that just something we're going to have to leave as a free parameter in our models?
So yeah, that's a very good question, and yeah, indeed. I mean, for sure, the mechanical part of the lithosphere, the crustal parameters that to some extent will drive how much of this melt would, and of course the properties of the melt itself, right, the density of the melts and so on, will drive how much of the melt can become extrusive and how much of the melt will remain stalled in the subsurface. I think it's not an easy question to ask, and I know that there are more localized regional models that look into this, especially looking at the melt transport through the lithosphere through this so-called two-phase flow, but also connecting that with formation of fractures. This all plays together in how much of the melt can actually in the end reach the surface, or how much of the melt remains trapped in the lithosphere. For this global thermal evolution models, of course, the challenge is to model this kind of processes that typically occur on much smaller spatial scales and shorter time scales in such a global model. I think in this sense, probably what would be needed in future work is to to have some kind of scaling laws derived from this more regional, more complex models that can actually accurately track melt migration, melt extraction, and use those scaling laws then to mimic this kind of processes in global scale models. But I think we're not there yet. So that's why what we have done in our model so far is to keep this as a free parameter and try to, looking at the thermal gradients that we have inferred from elastic lithosphere thickness, to try to constrain what is this fraction of intrusive to extrusive melt that can actually help us match, at least locally, this very high thermal gradients that we observe on Venus.
All right, great. Well, we're at the hour, so I guess all that's left to do is to thank Ina again for the fantastic talk and Q&A session afterwards. And I guess I'll just announce that the next Rocky World is going to be on May 7th at the same time as we had today. And it's going to be given by Shami Tsai. And you can always reach us on the Rocky Worlds Discord. And thanks all for coming. Thanks again, Ina, for the talk. And
thank you very